Thank you very much for being here. Today I'm going to tell you a bit about some of the work we've done looking at novel approaches to harnessing neuroplasticity as a means to improve cognitive outcome and actually foster brain repair in children with brain tumors. But I think the ideas behind this can be applied to other cancers and indeed other neurologic injury in children. I don't have any conflicts to disclose. What I'm going to do this afternoon is talk a bit about harnessing neuroplasticity for recovery and repair. Just give a brief highlight of some of the work we've done using activity-dependent repair, specifically exercise training, and how we've seen that fostering brain growth in children with brain tumors. I'm going to tell you about some recently completed work using the drug metformin to stimulate the stem cell niche in the brain and some exciting findings that we've seen there. And then perhaps talk a bit about a new paradigm that I think we should consider looking at as an oncology field in terms of how we treat late effects and maybe consider treating them in the same way we treat primary disease. So we know we know the effects of the tumor on the brain. There can be direct trauma. We know the effects of radiation and chemotherapy lead to a cascade of injury, including death of immature precursor cells, impairment of growth in new neurons and glial cells, disruption of the blood-brain barrier and inflammation. And this cascade of effects ultimately results in white matter insult and hippocampal and cortical atrophy, and I'll show you some examples of that. All of this, I think, ultimately leads to disrupted brain function and cognitive impairment. So we have a good idea now of what are the underlying, I think, neurobiological substrates of the cognitive late effects we see in children treated for brain tumors. You know, I think we have to acknowledge that we've actually seen significant improved outcomes from advances in primary therapy, particularly in radiation therapy. So what I'm showing you here is work that we did over 10 years ago looking at longitudinal intellectual outcomes following craniospinal radiation for medulloblastoma. And you see there's quite a significant decline in outcome. And what I'm showing on the right now is recent work that I did with Lisa Cahaley. This was a collaboration between Texas Children's and Sick Kids where we looked at two cohorts of children treated with proton therapy or photon therapy, protons at Texas Children, photons at Sick Kids. And you'll see, I would say, the dramatic improvement in outcomes. So certainly for photon therapy, we see stable intellectual outcomes, which was significantly different than photon therapy, where there continues to be a decline. But this, I think, state-of-the-art photon therapy also is much better than what it was 10, 15 years ago. So we have to acknowledge, I think, the significant progress that's been made in modulating our therapies to protect late effects, protect children from late effects. But I think there's still work that needs to be done. So, for example, we're going to hit that ceiling where we can't modulate therapy any longer, so that it's no longer effective is one thing. And two, we're still seeing certain late effects. So Lisa and I also found, regardless of whether kids got protons or photons, we still see declines in processing speed. And as we know, processing speed is a core cognitive function really important for academics and learning. And so I think we're going to have to look at novel therapeutic ways and to help the brain recover and actually help cognitive recovery in children. So to kind of give you a sense of what these underlying biological mechanisms of late effects are, I wanted to just kind of give you a couple visuals of some of the imaging that we've done. So what I'm showing you here is a diffusion-weighted image. And this diffusion-weighted image, we look at water diffusion in the brain and the directionality of water diffusion in the brain, and that tells us something about the underlying microstructure of white matter. This is an image where we have aggregated a core of white matter across all the population in the study, and that's this area of green, underlying green. So this is a white matter core. And all the areas of red are areas where there's a difference between healthy children and children treated for brain tumors. So even with our state-of-the-art radiation therapies, these are patients treated with craniospinal radiation, there's still diffuse white matter insult as measured by FA, fractional anisotropy. Another metric that we can gather from diffusion imaging is radiodiffusivity, which is probably a bit more closely aligned to myelin than fractional anisotropy. And you see the same thing. So the underlying core of the green is our healthy white matter, and all the areas of blue are areas where there's been compromise relative to healthy children. To take this further, another metric that we can look at is magnetization transfer imaging. Now, this is much more directly tied to myelin. Diffusion imaging is an indirect measure of myelin and white matter. Magnetization transfer imaging, by looking at the transfer of bound and unbound water in the brain, we can actually look directly at myelin. And so we're actually seeing significant myelin damage based on state-of-the-art photon radiation therapy. So there's still work to be done. We also see hippocampal cortical atrophy. So what we did here is we segmented the hippocampus in a group of healthy children and children treated with craniospinal radiation, and we segmented it into its subfields. The subfields of the hippocampus are known to be functionally distinct, and saw a number of areas where the hippocampus was smaller in volume, including the dentate gyrus. Keep that in mind as we go through the talk. CA1 and CA3. So these are functionally important areas of the hippocampus in memory formation, and we see decreases in volume. And this was work done by a former graduate student, Lexi Decker. So understanding the kind of neurobiological basis of these late effects raised the question, can we harness some of the more recent work done in neuroplasticity to mitigate these late effects? And so I would say in the last 10, 15 years, there's been a real shift in cognitive neuroscience and in developmental neurobiology, where we understand the brain is much more plastic than we had considered. And many more papers coming out talking about harnessing neuroplasticity and documenting the fact that you can see changes in white and gray matter as a function of learning to juggle, learning to play the piano. Kind of basic molecular studies showing that in an optogenetic model, if you activate neurons, you actually see myelination. That's work by Michel Monge at Stanford. Certainly the work done by the Swedish group, which I'll reference later, showing that running, which fosters neurogenesis, has an impact, positive impact. So really the question was, can we harness endogenous mechanisms in the brain for brain repair? So if we think about these endogenous mechanisms, we focused in on looking at neural precursor cells, the stem cells within the brain, and can we capture those stem cells for brain repair? So in humans, we talk about stem cell niches being in the subventricular zone as well as in white matter. White matter is a significant area of neural precursor cells, as well as the dentate gyrus in the hippocampus where active neurogenesis occurs. And you have the analogous stem cell niches in the mouse brain, in the rodent brain, including the SVZ, as well as the dentate gyrus. So it gives us an opportunity to mechanistically look at possible brain repair strategies in a mouse model and translate that to human studies. And so this has really led to the idea of, can we induce endogenous repair in the brains? Can we actually harness the natural processes of repair in the brain for therapeutic means? And I really have to acknowledge the work of my colleague Frida Miller and her husband David Kaplan, who really, I think, are proponents of this idea, and in a paper in Cell Stem Cell probably about 5 or 6 years ago really took this idea of, can we use things like experience-dependent activity, so learning, exercise, or can we actually find novel therapeutics and small molecules that will activate the stem cell niche, cause expansion, migration, and differentiation of neural precursors into functionally active neurons and glial cells? And this is where our work in the past 5 years has really targeted as can we use this approach in children treated for brain tumors? So I think one of the most well-known approaches has been the impact of cardiorespiratory exercise on neurogenesis in the dentate gyrus. And this has been known for a long time. So if you take a mouse and you put a running wheel in their cage, and this is work by Paul Franklin. So if you have a group that have a running wheel and they're allowed to run for 28 days versus a group that aren't allowed to run for 28 days, you see really significant differences in the birth of new neurons. This is lineage tracing histology, where you see very few new neurons in the non-running group, but significantly more in the running group. And this is also associated with increased memory performance. And indeed, I'll reference again the group from Sweden, where this was really an inspiration for me, this paper that showed that if you take radiated mice and you give them access to a running wheel, you see improved outcome after access to that running wheel and increased neurogenesis. So actually taking an activity-dependent activity has nothing to do with any kind of small molecule, just having them run more, and you see changes in the brain. And indeed, based on that study, we conducted an exercise trial in children treated for brain tumors. We took 28 kids. We had them exercise for 12 weeks in a structured exercise program 3 times a week for an hour and a day, and we each time of those 3 times. And we saw a number of things, including growth of white matter. So this is the same diffusion image that I showed you earlier. And now these areas of red are areas where there's been increase in fractional anisotropy, suggesting increased growth of white matter following exercise. And this was significant after training. And in fact, there was a carryover effect. 12 weeks after exercise training, we continued to see this improvement. We also looked at the hippocampus because it's a known stem cell niche, and one of the areas that we know based on the mechanistic studies is vulnerable to radiation. So we segmented the hippocampus, and we looked at changes in the size of the hippocampus, and there was an increase in volume, again as a function of training, and seen 12 weeks after exercise training. Finally, we looked at cognitive outcomes in these children. And here we looked at reaction time, how quickly they completed a series of tasks, and their speed got faster. So when we're looking at a change score here, this decrease means there's a decrease in the microseconds, which means they're getting faster. And again, we saw effect of exercise and the carryover after 12 weeks only in a group setting. So this was very exciting to us, suggesting that we can actually use something as simple as exercise to actually change the brain in the children that we see. Now, this is a small single exercise trial, and really the challenge is to ramp this up into something larger. And so what we're doing right now is, with the PhD student Elizabeth Cox, is building an online suite of tools that we can ultimately test and then pass on to various sites who are interested in providing an exercise program. And because really the goal is to make exercise as accessible as possible, and hopefully in years to come I'll be able to tell you about that work. So the other area that was exciting for us is looking at pharmacologically activating plasticity and really looking at the drug metformin. And this is work, again, done by Frida Miller, who is a neurobiologist at Sick Kids. And she kind of surreptitiously discovered that the drug metformin activates the atypical PKC-CBP pathway to promote neurogenesis and enhance spatial memory formation in healthy mice. And so if you look here again, this is the dentate gyrus in the hippocampus. And again, with cellular lineage tracing, where they mark stem cells and follow the lineage, you can see many more new neurons in the hippocampus, young neurons following treatment with metformin versus control mice. Further, they also observed improved behavioral performance and memory tests in this. Now, thinking about metformin, we said this is a fairly well-known drug. It's been used to treat diabetes for a very long time. And so we said, I think it makes sense for us to now go forward and look at this as a possible means to repair the brain following treatment for cranial spine treatment with radiation. And we did this in two ways. First of all, with my colleague Cindy Morshead, a neurobiologist at the University of Toronto, we conducted some preclinical animal studies looking at radiation, a radiation model, and the impact of metformin in animals who were treated with radiation. And so she irradiated mice at P17, and then she used a neurosphere assay, which basically looks at the fold increase in neurospheres that are bundles of stem cells on histology. And then she gave metformin to subsequent animals, and did also half the animals had a medium, a non-metformin medium. And then there was cognitive testing, and then the neurosphere assay at the end. And what she found was an increase in neurogenesis, again in the dentate gyrus. And furthermore, she saw a behavioral improvement on the Y-maze task, which is essentially a mouse version of a working memory task, where she saw basically recovery of performance up to control levels in the metformin and radiated treatment mice, in female mice only. So this is, we're starting to consider possible specific sex effects in the impact of some of our brain repair strategies. So we took this further based on this preclinical data and said, can we do a pilot feasibility study to look at, number one, is it feasible in terms of safety and feasibility to give metformin to children treated with brain tumors? And can we identify specific outcomes that may be sensitive to metformin effects that could be carried forward into a larger efficacy trial? And this is work done by Rami Ayoub, who's a graduate student in my lab. I also need to give a shout out to Eric Buffet, who I think as a qualified investigator on this trial really drove it forward and would not have happened without his support. So here's the schema. What we did is we looked at over 130 eligible participants. Ultimately, 24 participants were randomized to either two sequences, a sequence where they received metformin, then there was a 10-week washout, and then there was placebo, and this is 12 weeks, 10 weeks, 12 weeks, or a sequence where they received 12 weeks of placebo, 10-week washout, and 12 weeks of metformin. And we obtained a number of outcome measures, including safety measures in terms of blood work, adverse effect, medication adherence, as well as procedural adherence to the outcome measurement. We looked at a number of cognitive outcomes, including audio-verbal memory, visual-spatial memory, short-term memory, working memory, attention and processing speed. And we also looked at MR outcomes. Again, going back to the two main ones, we looked at diffusion imaging to look at white matter in the corpus callosum, as well as arterial spin labeling to look at blood flow in the hippocampus, as this might be a surrogate for neurogenesis. Here is the cohort, the groups between the sequence groups. There were some differences in terms of the actual intensity of the radiation they had, as well as whether they had mutism following surgery. So there were some differences between our two sequence groups, and we'll keep that in mind when we interpret our results. When we look at simply adverse effects, there we go. So we saw, what I would say would be the typical adverse effects associated with metformin in terms of GI symptoms, nausea, diarrhea, and vomiting. But we had no serious adverse effects, and no kid dropped out of the trial because of the adverse effects. And you'll notice, even on the placebo side, we saw increases in some of these adverse effects as well. We had high procedural adherence across all the outcomes, including our imaging and our cognitive outcomes, as well as medication adherence. Now, when we looked at the specific sensitivity of the measures we looked at, we saw evidence for increased verbal memory recall. So we had a sequence effect, meaning that the A, B, and the BA group had different impacts to metformin. And in the case of a sequence effect in the crossover design, what you need to do is only look at period 1 now, where you have simply the metformin versus the placebo. And when we did that, even though these are small numbers here, we saw a statistically significant increase in the number of words recalled in a verbal learning task, similar to the same type of task that the mice did in spatial learning. This is a hippocampal-dependent task. Furthermore, when we looked at a measure of working memory, we saw, again, when we had a sequence effect, and so we only looked at period 1 or cycle 1, we saw an increase in performance on the working memory task in our small sample, which is very compelling to me when we consider the preclinical mouse data where there was increased in working memory behavior associated with hippocampal neurogenesis. We also saw a decrease in reaction time, a similar measure that we used in the exercise trial, where we saw kids got faster. Again, we only looked at period 1 because of the sequence effect, but there was a significant decrease in how quickly they could complete these tasks. And finally, when we looked at our measure of myelination in the corpus callosum, we actually saw a treatment effect of increased myelination following treatment with metformin, which is interesting because previous preclinical studies that Cindy did that I haven't shown you showed increased oligodendrogenesis in the corpus callosum in a hypoxia ischemia model following treatment with metformin. So I think these are very preliminary results, but the confluence and the parallels of findings between the mechanistic animal studies and the pilot human studies are very exciting for us. So, just right on time. I think what we've demonstrated is that metformin shows promise for improved memory and speed of processing in children treated for brain tumors. So a clinical trial is feasible. This was in a very small pilot trial at a single institution, but we had excellent medication and procedural adherence. It was tolerable in brain tumor patients. No kids dropped out because of adverse effects. We had no serious adverse effects, the main one being lactic acidosis, no evidence of lactic acidosis. This is a very small pilot trial, but excites me because of the confluence that we're seeing the same types of effects in these mechanistic mouse studies and in the human studies. And so what we need is a larger efficacy trial, and we're currently seeking funding for that in a larger consortium of Canadian, North American, and Australian centers, including Sick Kids, Children's National, St. Jude's, Memorial Sloan Kettering, Lucille Packard, and Melbourne. So kind of just in the final few minutes, I want us to stop and just kind of reflect on how we address late effects in children treated for brain tumors, and in fact, how we address late effects in pediatric cancer in general. And I think we kind of have a history of simply in many cases, at least in terms of neurocognitive late effects, of simply documenting these poor outcomes. And that's led us, I think, a long way. I think because we've documented them, we've seen treatment changes for the primary disease that have allowed us to reduce those. But we also need to start thinking about management and compensation. So how can we help children in school to manage, so the actual child who has now experiencing the effect, how can they manage and compensate? But I think now we're entering an era of active treatment and brain repair in children. And I think this, I envision this as kind of combinatorial, multimodal, late effects clinical trials in the same way that we treat primary disease. I think we're at the point now where we have various strategies that we can apply to address late effects. Where did the big advances come in treatment of pediatric cancer? They came when we started to combine various modalities, and that's when we saw the greatest increase, I think, in the cure rates. And I think the same can potentially be true. Oh, perfect. When we combine things like early prevention, some of the work that people are doing trying to prevent mutism, the pharmacological and cognitive rehabilitation studies, like CogMed, and brain repair and brain protection studies like metformin, start to think about how can we combine these at the right time for the right child in order to actually improve their outcome following treatment. I need to acknowledge the members of my lab, including Cynthia Demetrios, who did much of the clinical trial work, and Jovenka Skosik. Liz Cox is doing the exercise work. I need to acknowledge my collaborators, the therapists involved in the exercise work. I need to acknowledge my funders. And I thank you for your attention.